Good morning all. This is Dr. D. Khalandar Basha, working as Associate Professor in the Department of ECE, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss few programs related to 8086 processor. In this series, we are going to see the assembly language programs for multi-byte addition, multi-byte subtraction, and to find the sum of squares under the course microprocessor and microcontroller. The slides are prepared by referring the textbook Advanced Microprocessor and Peripherals. Authors are K.M. Gurchandi and A.K.R.E. Publication Tata Micra. The first program is to write an ALP for multi-byte addition. So here we are going to take two values that I can take the data 1. The second one is data 2. As it is multi-byte, so some value we are going to take. So in this example, I am taking 4 bytes. This is byte 0, byte 1 and byte 2, byte 3. Similarly for data 2, we are going to take a 32-bit data, which is 4 bytes. These data we are going to be stored in the memory. So this memory slot is for data 1. The next 4 memory locations for data 2. Next we have reserved for sum of the data 1 and data 2. So after addition, the byte 0 of data 1 is added with the byte 0 of data 2, that it is going to be stored in sum byte, that is S0 byte. Next we will fetch the byte 1 of data 1, byte 1 of data 2. By addition of these two, we are going to get S1 byte, that is sum byte 1. Next we will add the contents of data 1 byte 2 added with the data 2 byte 2, and the sum produced is S2 byte. Next we will fetch the byte 3 of data 1 added with the byte 3 of data 2. The sum which is produced, that is S3 byte, is going to be stored in the sum location. So in the data segment, this is data segment. First one we will take as byte 1 of series, byte 1 of series. It is going to have D1 byte 0, D1 byte 1, D1 byte 2, D1 byte 3. These are 32-bit of data 1. The next data we are taking as byte 2 series, where the address here it is points to the data 2 byte 0, the data 2 byte 1, the data 2 byte 2, the data 2 byte. As we are considering 4 bytes, the addition will be repeatedly executed for 4 times. So for that we are going to be place count, which is 4 in the next memory location. After that next memory location, we are going to have the sum. So this is for sum of the sum byte I can take, where we are going to have a sum of byte 0, sum of byte 1, next sum of byte 2 and sum of byte 3. So this is what the data segment which we are going to be used in the program. Now we will see the explanation step by step, then we will see the program at a glance. So in the program, as the memory for data segment will be assigned by the assembler, the address assigned for data segment will be fetched by using the first two instructions, that is move AX comma data, where data is consist of the address of the data segment. As 8086 will not support for loading the immediate data into the segment register, first we will place the address of the data segment into AX register, from AX register to data segment register. Move AX comma data, move DS comma AX. The purpose of these two instructions is for loading the data segment register with the data segment address assigned by the assembler. Next, in the data segment, we have defined few locations. The first location, it is for byte 1 series. For fetching the address, that is nothing but offset value of this variable byte 1 series into SI register. So for that we use the instruction move SI comma offset of byte 1 series. This instruction will load the SI register with the offset of the byte 1 series. Similarly, for byte 2 series, we will fetch the offset using the direct to offset that will be loaded into the BX register by using the instruction move BX comma offset of byte 2 series. This instruction loads the BX register with the offset value of the second variable of the series, that is byte 2 series. Next, we will fetch the address, nothing but offset value of the result where we want to store, that will have the byte underscore sum as a variable name. So that offset value we will load into DA register by using the move instruction DI comma offset of byte sum. So this instruction load the DA register with the offset value of the byte sum. Next, how many times we are going to be repeatedly add that count we are going to be load into CL register. So for that we use the instruction move CL comma count. The next one is we will fetch one data from byte 1. So this is the memory. Here we have byte 1 4 memory locations. Next, byte 2 4 memory locations. Next we have count. After that we have sum byte. So for fetching the address of the first data, we are going to be load that one into AL register. For fetching the content of the byte 1, byte 0, we use move AL comma in brackets SI. So this will indicate the contents of the memory location whose address is specified into SI register, that contents will be loaded into AL register. Next, the second byte which we are having BX. This BX is pointing to byte 2, SI is pointing to byte 1. So the byte 0 of byte 1 by the byte 0 of second data 2, we are going to be added by using the add AL comma in brackets SI. So this instruction will add the AL contents with the contents of the memory location which is having address in the BX register. The result will be stored in AL register. So whatever the result which is obtained after adding the 0th byte of data 1, data 2 will be loaded into the destination locations. So after addition, we have the result AL. That AL contents will be loaded into the destination address where DI is pointing to the some variable. So this we have added 1 byte of data 1 with the data 2. The result is placed in some location. Now we want to go for the second byte, that is byte 1 of first data with the byte 1 of second data. So here we have to advance the address. So for that we go for incrementing the address in SI register by using the increment SI. This is mainly to increment SI register. The purpose is to fetch the second data, we have to point to the next memory location which is there in the SI register. Similarly, increment BX. This is for fetching the next byte of the byte 1 series. Similarly, we have to place the byte 1 into the next memory location. To advance to the next memory location, we will increment the DI also. So by using increment DI, this instruction is used for incrementing the DI to fetch the address of the next byte where we want to store. As one byte addition is done, so we are going to decrement the count which is there in the CL. So this iteration will be repeated until the CL content is equivalent to 0. So for that we are going to check JN check loop 1. So when the CL contents are not 0, then it will be goes to the label 1. Otherwise, subsequent instruction will be executed. In this program, we are going to add byte 0 of D0 will be added with D1 of byte 0. After this addition, then we go for D0 by byte 1 and D1 data byte 1. After that, D0 byte 2, D1 byte 2. Then D0 byte 3 and D1 byte 3. So here we are going to add the addition operation for 4 iterations. So these iterations we are going to be loaded in CL register. So for every iteration, the CL content will be decremented by 1. So once the count is 0, it indicates all the addition is done. So we can come out of the loop. So then we are going to terminate the program by raising INT21H. Suppose if count is non-zero after the first addition, then we have to advance to the next addition. So for that we are going to label 1. So where label 1 is specified is here. Fetching the data from the data 1. Similarly, second data. Repeatedly we go for addition and storing the result. So once the CL content is 0, then we will come out of the loop. So in the loop, once it is done, entire data is added. So we can terminate the program by returning to the DOS. So for that we use the instruction move AH, 4CH and we will raise int 21H. Now we will see the program at a glance. Assume CS colon code, DS colon data. This assembler directive is used for accessing the address of code segment and data segment which is assigned by the assembler. Next we will write the data segment and code segment. In the data segment, as it is a startup segment, we use the directive segment to decide with what type of segment we are starting. This data segment is consist of multiple values. One is byte 1 series followed by byte 2 series, then count, after that sum. So we are going to reserve how many memory locations we are going to be stored is 4 locations we have to store, because after addition of byte 0, byte 1, byte 2 and byte 3. DUP question mark, it is for only reserving the memory. Question mark indicate it is uninitialized. Next we will end the data segment by using the directive data endes. Endes is the directive it is used for ending a particular segment. Now we will start the code segment by using the segment directive to proceed with the code segment, start of the program. First we will load the data segment address assigned by the assembler into the DS register. For that move AX, data, move DS, AX. Next we will fetch the first byte of the series into SI by using move SI, offset of byte 1 series. Similarly for byte 2 series, offset value will be loaded into BX by using MOV BX, offset of byte 2 series. Next the address of the target location that we are going to be stored byte underscore sum offset value into DA register. How many times or how many bytes we are adding, that we are going to be loaded into CL register. For fetching the content of each memory location of the source byte and byte 1 and byte 2, we are going to use move AL, SI. This will fetch us byte by byte of the first data into AL register. The next instruction, we will add the first byte of data 1 with the first byte of the data 2 and it will be repeated for 4 times. Once the addition is done, the result is in AL that we are going to be loaded to the destination location which is assigned for sum. For advance to the next memory location, increment SI, increment BX, increment DI. This is for data 1, data 2 and this is for sum. As one iteration is done, we are going to be decrement CL. If the CL content is non-zero, go to label 1. So in the label 1, we will write the instruction for fetching the data. So this loop from L1 to J and Z will be repeated for depending upon the count we are specified in CL register. In the example, we are considering the CL content as 4 bytes, that is CL is equivalent to 04. So once the CL is equivalent to 0, we will terminate the program by returning to the DOS by using the instruction move AH, 4CH, INT 21H. For ending the code segment, we will use the directive endes corresponding to the code. So we will write the statement as code endes. To end the program, we use the directive end. The start of the program is with the label start. So end start. So this is the program for a multi-byte addition where we are going to take a two data 0 and data 1, which is of 4 bytes each, that is 32-bit data. After adding each by bit, we are going to be storing the destination. Now we will move to the next program where we are going to do the subtraction. In this subtraction also, we are going to take the data that I will take as data 1. The second one is data 0. This data 0 is consist of 4 bytes B0, B1, B2, B3 of data 0. Similarly, the data 1 is consist of 4 bytes, byte 0, byte 1, byte 2 and byte 3. Here, the contents of data 1 will be subtracted with data 0. So that is the data 0 minus data 1. We are going to subtract. Whatever the difference we are going to have, this difference we are going to allocate some memory location where we are going to store byte 0 of data 1, data 0 will be subtracted and we'll get the result, that is difference byte 0, byte 1, byte 2, byte 3. So here we are going to perform the subtraction 4 times. So the count we are going to be space is 04H. Now we will see the program step by step. As the address for data segment will be assigned by the assembler, we will fetch that instruction and we will store that address into the data segment register by using the two instructions, that is move AX, data followed by move DS, AX. As 8086 is not supported for moving the immediate data into the DS register, so immediate data first we will load into AX register, from AX register to the data segment register will go. Next, for fetching the address of byte 1 series, we use the instruction move SI, offset of byte 1 series. So this instruction will fetch us the offset assigned by assembler for byte 1 series will be loaded into SI. Next, for the second data, we use the instruction move BX, offset of byte 2 series. This instruction, it is used for fetching the offset value for the byte 2 series that will be loaded into BX register. Next, for the result which you are going to be stored in the memory, that address will be fetched in the next instruction, that is move DA, offset of byte difference. So this instruction will fetches the offset value for the variable byte difference that will be stored into the register. As we are having multi-bytes, how many number of bytes we are having, that count we are going to be loaded into CL register. Next, we will fetch the byte 1 series first content and subtracted with byte 2 series, and the result will be stored in byte difference. Move AL, in square braces SI. This instruction is used to fetch the byte by byte for data 0 into AL. Next, we will subtract D0 with D1 content for each and every byte by using SUB AL, in brackets BI. So this instruction will subtract AL content with the content of the memory location which is pointed by BX register, and the result will be stored in AL register. What are the difference which we have obtained here? That we are going to be stored into the memory. That memory address is loaded into the DI register. So move in square braces DA, AL. So now this AL contents will be stored into the memory location which is pointed by byte difference. For each iteration byte 0, next iteration byte 1, next iteration byte 2, next iteration byte 3. Like this it is going to be stored. Next, for advance to the next memory location, we go for incrementing SI, incrementing BX, for this is for data 0, this is for data 1. Similarly for byte difference variable for increment DI. As one iteration is done, we have to decrement the count which is there in the CL register by using the instruction decrement CL. So this loop will be iterated until the CL is equal to 0. So for that we go for conditional control instruction with this JNZ CL. So if the CL content is non-zero, then that indicates still some more operation we have to perform, the data is available. So we go for label 1. Otherwise, that means if CL content is 0, it indicates all the data are subtracted. So we can terminate the program by executing subsequent instruction, which is for returning to the DOS. Move AH, 4CH and generate 21 type interrupt by using INT 21H. This is the program for multi-byte subtraction. Now we will see the program at a glance. Assume CS colon code, DS colon data. This assume directive, it is for fetching the address assigned by the assembler for code segment and data segment into CS and DS respectively. Next, we will start the data segment by using the segment directive. As it is data, it will be preceded by data. So it will indicate the start of the data segment. In this, we are going to have multiple variables like byte 1 series, byte 2 series, then how many values we are having, that is count, byte difference, which is DB 04 because 4 bytes are required, and DUP, it is for reserving the memory without any initialization. We can end the segment by using the end as directive. That is corresponding to the data, we will precede this one with data end as, indicates it is the end of the data segment. Now we will start the code segment by using the directive code segment. Segment is the directive which is used for start of a segment. As it is corresponding to the code segment, we will precede this one with code. Next, start of the program with the label start. First, we will load the address assigned by the assembler for data segment into the data segment register. Move AX, data followed by move DS, AX. As immediate data is not allowed to load into the segment registers, we go for loading the immediate data into AX register from AX register to data segment register. Then we will fetch the address of the byte 1 of the series into the SI by using the instruction move SI, offset of byte 1 series. Similarly into BX, offset of byte 2 series, and DI register will hold the offset of the byte of the difference. How many times the bytes we are going to be subtract, that count we are going to be loaded into CL register. Now we will start the program by fetching each and every byte from the byte 1 series as well as byte 2 series. After doing subtraction, we will move the data result into the difference byte. For fetching the data, move AL, SI. This will fetch us byte by byte of the byte 1 series. Next, we will subtract this byte 1 series data with the byte 2 series by using SUB AL, in brackets BX. Here also byte by byte of byte 1 series subtracted with byte 2 series. Whatever the difference which is obtained in AL register, that it will be loaded into the target location by using move in square braces DA, AL. For advanced to the next byte, we go for incrementing SI, incrementing BX, incrementing DI. Next, as one iteration is done, we have to decrement the count, that is decrement CL. If this count is non-zero, that CL contents are not zero, go to the label 1, where label 1 it is used for fetching the data from SM location. Once the count is 0, it will come out of the loop, where we can terminate the program by returning to the DOS by generating the interrupt 21H. Before that, for return the DOS, we have the subroutine at 4CH. So we will write move AH, 4CH followed by INT 21H. Then we will end the program segment, that is code segment, with the end as directive, preceded with the code indicating it is the end of the code segment. Then we will end the program by using end directive. The starting label is start. So this is program for multi-byte subtraction. We will move to the third program. Under this, we are going to write an assembly language program to find the sum of squares. Here also we will take a series variable where it is going to consist of multiple bytes. I am going to take the 32-bit data. The objective is what are the series we are going to take. For this we have to find out the square of this particular number and we have to add each and every byte. So we will fetch B0. B0 will be multiplied with the B0 that it will be stored into the destination location, where the destination location we may have like the sum of the squares. Then we will fetch B1 contents. B1 content will be multiplied with the B1 and the result will be stored in sum of the square SS0 and this one is S1 I will take. Next we will fetch B2. B2 will be multiplied with the B2 and the result which is obtained, the product that we are going to be stored as SS2 in the target location. Next we will fetch the B3 byte. This B3 byte will be multiplied with the B3 byte. The result which is obtained that I am taking as SS3 that will be loaded into the target location. So before going to the program, just we will revise what is a mull instruction syntax. So the mull instruction is syntax is operand 1, where it is going to support 8-bit by 8-bit multiplication as well as 16-bit by 16-bit multiplication. Now in this example we are going to be considered 8-bit by 8-bit multiplication. One 8-bit is there in the AP operative operand 1, whereas the second operand is implicit operand that will be there in the AL register. After multiplying this AL contents with the operand 1, the result is a 32-bit size, a 16-bit size. So 16-bit the product we can see in AX register. As we want to take the sum of the square, here operand 1 and AL should be same. So for that we are going to take operand 1 as AL. So then AL will be multiplied with AL, which will use the square of the number. That result we can see in AX register. The product. Now we will see the program step by step, then we will see collectively at a glance. The first instructions are for loading the address assigned by the assembler for the data segment into the data segment register by using two instructions, that is move AH, data followed by move DS, AX. At 8086 processor, you will not support loading the immediate data into the segment register. So first we are going to be load the immediate data into AX register. From AX register to the data will be loaded into data segment register. For clearing, we are going to use XR BX, BX. It is for clearing the data because we need to find the sum of the squares. After each and every iteration, once the square of the sum is done, that will be added. Next, whatever the series variable is there, so for that whatever the offset is assigned by the assembler, that will be loaded into the SI register by using move SI, offset of series. This instruction will fetch us the offset value of the series variable that will be loaded into SI. Move CL with the count. So in this example, how many values we are going to be considered, how many bytes we are going to be take, that we are going to be loaded into CL register. Then move AL with the fetched data of the series. So the address of the series is in SI. That memory location contents will fetch indirectly by using the square braces of SI. This data will be loaded into AL. So now the byte is there in the AL register. So now for finding out the square of this number, we use mul AL. So this mul AL instruction will multiply AL contents with the AL contents and the result will be there in SI. AX register. So for each and every byte, we will find out the square of it. Similarly for byte 1, for each iteration, then byte 2, then byte 3. So we have to add all these values. So for that initial sum we will take as 0. For that purpose we have cleared the BX register. So for BX, we are going to add the product which is there in the AX. So add BX comma AX. So this instruction will load the BX register with the addition of BX register with the product which is there in AX register for each iteration. As one byte is done for sum of squares, then we are advancing to the next byte. We go for incrementing SI. Then decrement as count we have placed in CL register, and one byte we have found a square, we have to decrement the count. So for that we use the instruction decrement CL. So this loop has to be iterated repeatedly until the count is equivalent to 0 in the CL register. So when the count is non-zero, we have to go for the loop. So for that we use JNZ instruction. So this JNZ instruction will check whether CL content is 0 or non-zero. If CL content is non-zero, then it will be go to the label L1. If CL content is 0, indicates all the contents are squared and it is added to the default sum. So we can terminate the program by returning to DOS. So L1 we have placed for fetching the data, that is move AL comma SM. So this loop will be iterated until CL is equivalent to 0. Once CL is equivalent to 0, this loop will be terminated. It will execute the subsequent instructions which are for terminating the program by loading the sum into the result variable. So for fetching the address of the sum of the squares into DA register, we use the instruction move DA comma offset of sum of squares. So this instruction will fetches the offset value of the sum of squares into DA. Previously when we have added the content where we are having the result in BX register, so that BX register contents we are going to be loaded into the memory location. So for that you'll write move in square braces DA comma BX. So now the BX contents are loaded into the memory where memory address is placed in DA register. Then we will terminate the program by using move AH comma 4CH and INT21H. These two instructions for returning to the DOS. Now we will see the entire program at a glance. Assume CS colon code comma DS colon data. This is for requesting the assembler to assign the address for data segment as well as code segment that will be stored in code and data respectively. To start the segment, we use the assembler directive, that is segment. As it is corresponding to the data, we will write data segment. In this segment, we are going to have a few variables. The first variable is series, DB, some values like 65H, 89H, ABH and 52H. So in the memory, the data will be stored in this fashion. In the first location 52H, the next memory location ABH, next location 89H, next location 65H. This will be pointed with the variable name series. After that, we are going to define a count. The count is 04. After that, we are reserving two memory locations of 8 bits with uninitialized. So for sum of squares. So after finding out square and adding to the squares, we are going to get the result in this memory location. We will end the data segment by using the end dash directive preceded by data. So this directive is used for end of a particular segment. Next, we will start the code segment with the directive segment. Segment will use the start of a segment as it is preceded with code. So this is corresponding to the code segment. We will start the program with the label start. The first instruction for fetching the address of the data segment that will be loaded into the data segment register. Then we will clear the BX register by using XOR BX comma BX register. For fetching the offset value of the series, we use move SI comma offset of series. Then we will load the count into CL register by using the instruction move CL comma count. Next, we will fetch the byte by byte from series variable by using the instruction move AL comma in square braces SI. So the memory location contents are loaded into AL. Now we will find the square of the number by using mul AL. So this instruction will multiply the AL contents with the AL contents and the result will be there in AX register, which is of 16-bit size. So after finding out the square, we are going to add to the default sum that is in BX register, initialized it with is 0. So now we are going to be add bx comma ax. So this instruction will add the previous sum with the sum of the square of a number. That result will be stored in bx register. For advanced into the next byte, increment si, then decrement cl. So this loop has to be iterated depending upon the count which was specified in cl register. So for that you will write j inject l1. So if cl contents are non-zero, go to label 1. Else, that is, if cl content is 0, go to subsequent instructions. In the subsequent instructions, we will fetch the address of sum of the squares variable. That offset value will be loaded into the DI. The result which is there in the BX register, that BX register contents will be loaded into the memory location whose address is specified in DI register. Then we will terminate the program by raising interrupt 21H, which is belongs to return to DOS by moving 4CH into AH register. Move AH comma 4CH INT 21H. Then we will end the segment by using the end dash directive. As it is corresponding to the code segment, we will write code endes. Then we will end the program by using the end directive, and the start of the program we have the label is end start. So thank you all. So in this part of programs, we have discussed the programs for multi-byte addition, multi-byte subtraction, and sum of squares. In the multi-byte addition, we have considered two datas, each of 32-bit size. We are going to add byte by bit. After adding each byte, the result, that is sum, we are going to be stored into the target location. The second program is about subtraction. The two datas, data 1 and data 2, we are considered as multi-byte, which is of 32-bit size in this example. The data 1 contents are subtracted with the data 2 contents byte by byte. After difference, whatever the difference is obtained, that we are going to be loaded into the target location. In the third program, to find the sum of the squares, so we are considered a series of numbers. We will fetch one data at a time. We will find out the square of a number that will be added with the default sum which is there in the BX register. The product is there in the AX register. These two contents will be added. So this loop will be iterated till the number of bytes which are specified in the series variables is equal to 0. Once all the bytes are fine for sum of the square, the result we are going to be stored into the target memory location. Okay. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.